Hi, my name is André. I'm from Universidade Tecnológica Federal do Paraná, Brazil, and I'm gonna present the paper NodeRacer Event Race Detection for Node.js applications. So this is a joint work with Anders Muller, and this research was conducted during my time at the Center for Advanced Software Analysis in Aarhus University, Denmark. So this research is in the context of Node.js, which is a JavaScript runtime launched in 2009. Uh, its main goal was to bring JavaScript on the server side, and so that we can quickly build and deploy applications. So with Node, it's possible to develop server-side applications, CLI tools, and support desktop and mobile apps, and so on. Node has a package manager called npm, and today you can find in npm more than 1 million packages. Uh, so there are many software applications powered by Node.js, and Node.js together with npm packages compose the largest software ecosystem in the world. Node adopts a single thread asynchronous model in which time-consuming tasks like I/O, compression, cryptography are performed asynchronously. So you register an event for these time-consuming tasks and an associated callback. Even though it's a single-thread model, Node applications are subject to event races, and these races are caused by non-deterministic callback interleavings. Uh, such interleavings may provoke a fault behavior or a race bug. So the system can crash, process or request can hang, and it's possible to persist inconsistent data and so on. So such bugs are prevalent in Node.js applications, and as it has been investigated in the literature. Here is an example inspired by a bug that we uncovered using NodeRacer. So we have a function in line 4 called processFile. This function starts two asynchronous operation lstat in line 6 and read file in line 12. For each asynchronous operation, two callbacks are registered, stat in green and read in blue. The function also uses variables, done tasks, and entries in line 1 and 2 to decide in line 15 and 16 if function finalize can be invoked. So here we have a test case that call the function process file 3 times for an existing file, for a missing file, and for an empty file. This code fires the execution of 5 callbacks represented as boxes, 3 times for stat and 2 times for read. Notice that callback stat comes before the read when the same file is processed. The missing file has only the stat callback, and ordering between the stat and read callbacks exists only for the same file. This slide shows the behavior when running this test several times. So in ordinary runs in a test environment using vanilla nodes tends to show uh, very few variations between the callbacks or no variation at all. So typically only little variation in the interleavings. Yet this code has a bug, but the interleaving that reveals the bug is very unlikely. In this example, the stat callback for the missing file, in this case stat2, needs to be postponed so that it's the last one to execute. This case, function finalize is not called and the system hangs. These interleavings are unlikely to occur at the development time, but it can occur in production due to a busy environment. Moreover, such cases are hard to reproduce and debug. We observed that several race-related issues remain open for quite some time, and developers keep trying to figure out what's happening. Therefore, we want an approach to exercise those interleavings, potentially revealing bugs while we respect the order among the callbacks. So our take is an approach called NodeRacer. Its key idea is to run the test in a guided execution where events are selectively postponed to explore more interleavings. Besides, the execution needs to be guided by a happens before relation. So this approach can be implemented entirely in JavaScript. So no changes are needed in the internals of the Node.js runtime. The input for NodeRacer is a script or a test that performs a potential race behavior. So NodeRacer is divided into three main phases: observation, happens before identification, and guided execution. We are going to explain each one of them next. In the first phase, observation, NodeRacer uses code instrumentation, to track the asynchronous behavior of the application. The idea is to leverage the async hooks API and a library called NJS trace to generate a log file with entries for events of interest. In the second phase, happens before identification, the log file produced in the previous phase is scanned and 9 rules are applied to identify happens before relation between the callbacks. 4 rules are drawn from the literature and 5 rules were proposed to model happens before in Node.js more accurately. All rules are fully described in the paper. The output of this phase is the 8B graph, or happens before graph, as is illustrated in this slide. In this graph, callbacks are nodes and edges represents happens before relation between the callbacks. Finally, in the third phase, NodeRacer instruments the callbacks and use happens before relation as a guide. So the goal here is to explore alternative callbacks interleaving by selectively postpone callbacks. The guided execution handles mainly three cases. The first one is when no interleaving is possible. For example, during the execution, callback full, represented as a gray node, is scheduled to run. And according to the 8B graph, it may not interleaving with any other callback. So for this case, NodeRacer let it run, remove it from the graph along with its outgoing edges. So we remove the dependence of the full callback. In case 2, the guided execution may postpone the current callback. For example, async p2 in gray is scheduled to run, and observe that it may interleave with async p1 and async p2 because these nodes have no dependency. For this case, NodeRacer handily decides to postpone p2. Finally, in case 3, the current callback cannot run due to some dependence, so the callback is postponed. For example, async p2 in gray is scheduled to run, but it depends on async p1 that it's not executed yet. So NodeRacer postpone async p2 and expects async p1 to run first. Using this guided execution, different interleavings are explored in each rerun of the original test. In the evaluation of NodeRacer, we investigated 4 research questions. In research question 1, we compare NodeRacer with the state-of-the-art fuzzer NodeFuzz, and using benchmarks of confirmed race bugs, we observe that NodeRacer has a better bug reproduction rate and review bugs with fewer runs than NodeFuzz. Moreover, NodeRacer runs on more benchmarks and can uncover a bug not revealed by NodeFuzz. For research question 2, we want to know if the use of happens before relation prevents infeasible executions and avoid needless delays. To do so, we implement a naive approach that did not employ happens before, and this naive approach was implemented on top of NodeRacer. The results gave evidence that the happens before guided approach of NodeRacer prevents infeasible callbacks interleavings. It also reduced the likelihood of false alarms. More than half of the failures by this naive approach involve a happens before violation. For research question 3, we look at the usefulness of NodeRacer in diagnosing race-related issues. So by investigating 5 open issues in GitHub, we note that NodeRacer is helpful to diagnose race issues. If there is a suspicious test scenario, it supports the reproduction of different interleavings, as well as the understanding of the ordering or lack of between the callbacks. Finally, research question 4 analyzes NodeRacer in the wild. So we run NodeRacer with 159 tests that have some interleaving from 8 different open source projects. We found 3 unique bugs and 2 flake tests. So if the existing tests create scenarios with potential interleavings, NodeRacer can exercise them to review previously unknown bugs and flake tests. Concluding, event races may cause many errors in Node.js applications. Our approach intends to boost existing tests using controlled execution that is guided by happens before relation. NodeRacer follows a lightweight approach that is implemented entirely with code instrumentation. It's important to say that no change to the underlying Node.js system is required. The experimental results gave evidence that NodeRacer finds event race errors with higher probability than a state-of-the-art fuzzer and produces actionable error reports. More details about this research can be found in the link. You may also scan the QR code. There you have pointers to the preprint, the source code of the tool, as well as the replication package. Now, I'm glad to answer your questions.